For much of recent history, the worlds of energy and digital technology developed along parallel but distinct paths. Utilities focused on generating and delivering power, while technology companies concentrated on computing and data. This separation is rapidly changing. The rise of artificial intelligence has driven an unprecedented demand for electricity, with tech companies now ranking among the largest consumers of power globally. As a result, the boundaries between technology firms and energy providers are becoming increasingly indistinct. This convergence is reshaping both industries, prompting new collaborations and challenges as they adapt to a more interconnected future. A new clean energy alliance is emerging, fueled by the convergence of small modular reactors, or SMRs, and hydrogen production. These technologies are being combined to address the significant energy demands of the rapidly expanding digital economy. Previously, nuclear power and hydrogen operated in separate spheres, but today, their paths are intertwined by the forward-thinking goals of technology companies. This partnership is not only transforming how energy is produced and consumed, but is also reshaping the future of both the nuclear and hydrogen industries. The story begins with the explosion of AI workloads. Training a large AI model requires staggering amounts of energy, sometimes hundreds of megawatt hours over days or weeks. Running that model afterward across global cloud platforms requires even more. Google, Microsoft, Amazon Web Services, and Meta collectively operate thousands of data centers, each filled with tens of thousands of servers, GPUs, cooling systems, and networking gear. The rise of large language models, generative AI, autonomous robotics, and cloud computing has transformed these facilities into some of the world's largest continuous electricity loads. Some analysts estimate that data center demand could double by 2030, and AI workload demand could grow even faster. The problem is simple. The grids of the world were not built for this kind of load. In the United States, power demand is growing faster than utilities can supply. In Europe, grid congestion has reached critical levels. In Asia, new data center clusters are competing directly with heavy industry for electricity. This is why tech companies are rethinking their entire relationship with energy. At first, big tech focused on buying renewables, solar farms, wind farms, and long-term clean power purchase agreements. Companies like Google pioneered the concept of 24/7 clean energy matching, attempting to align every hour of their electricity use with renewable production. But as renewable capacity expanded, the limitations became impossible to ignore. Solar works when the sun is out, wind works when conditions allow, and both vary dramatically across seasons. Data centers don't turn off at night. AI workloads don't pause when clouds roll in or when wind dies down. Big tech realized they could not rely on weather-dependent power alone, not if they wanted to scale AI to the next level. They needed firm, dispatchable, clean electricity that operated continuously and could be located close to their data centers. This is the moment when nuclear re-entered the conversation, not as a legacy technology, but as a strategic enabler of the digital future. Small modular reactors instantly grabbed big tech's attention. Unlike traditional nuclear plants, which are massive, expensive, and take decades to build, SMRs are compact, factory-built reactors designed for rapid deployment. Many designs operate between 10 and 300 megawatts, the perfect scale for powering individual data centers or clusters of them. They can be placed close to load centers, reducing transmission barriers, and they operate at extremely high capacity factors. And most importantly for companies obsessed with reliability, they provide clean, stable power literally 24 hours a day. Google became the first major tech company to signal serious interest by partnering with Oklo, an advanced nuclear startup backed by Silicon Valley investors. That relationship was more than a symbolic gesture. It indicated that big tech was ready to explore nuclear energy as a real asset class. Around the same time, Microsoft invested in fusion company Helion and began analyzing SMRs as part of its long-term power strategy. Amazon initiated talks for nuclear power procurement for its data centers. Even Meta has begun exploring next-generation energy systems to meet future AI demand. The message is clear. The digital giants are preparing for a world where nuclear power and AI evolve together. But what makes this all even more revolutionary is that SMRs do not just produce electricity. They produce heat, and lots of it. That heat is the missing link in the hydrogen equation. For years, the hydrogen industry has struggled with the economics of electrolysis. Electrolyzers work best when they run continuously, but renewable-powered hydrogen plants, tied to intermittent wind and solar, often operate at low utilization rates. That drives up cost and reduces efficiency. High-temperature electrolysis, especially solid oxide electrolysis, becomes dramatically more efficient when supplied with heat. SMRs produce that heat for free as a natural byproduct of their operation. Instead of using electricity to heat water for electrolysis, the system can use nuclear heat, cutting electricity demand and improving efficiency. Some advanced SMR designs can operate at temperatures above 600 degrees Celsius, ideal for high-temperature hydrogen production. Others can power thermochemical cycles that split water directly using reactions activated by heat. This synergy between nuclear reactors and hydrogen systems transforms what hydrogen production looks like. Now picture what happens when a tech company pairs an SMR with a data center. During peak AI demand, the SMR powers the data center. During off-peak hours, like nighttime when GPU clusters run lighter workloads, the excess electricity and heat can go into hydrogen production. Instead of wasting unused capacity, the energy is converted into hydrogen that can be stored, sold, or used on site. Suddenly, a data center stops being just a power-hungry facility. It becomes an energy hub. The SMR supplies baseload power, while hydrogen becomes the medium for storing excess energy or powering backup systems. Data centers today rely on diesel backup generators, thousands of them worldwide, creating a massive emissions problem. Hydrogen fuel cells could replace those generators entirely. SMR heat and electricity could produce that hydrogen on site. It's a complete transformation of how digital infrastructure interacts with clean energy. This pairing is not speculative. It is already being discussed in the corridors of big tech and major energy players. Google's interest in advanced reactors sparked conversations about integrated energy campuses. Microsoft has quietly been hiring nuclear engineers and hydrogen experts. Amazon has been exploring energy models where data centers are co-located with clean hydrogen hubs. The reasons are compelling. Hydrogen gives tech companies something renewables alone cannot: long-duration storage in a chemical form. Hydrogen can be turned into ammonia, methanol, or synthetic fuels. It can power heavy-duty vehicles, logistics fleets, or industrial equipment. It can provide emergency backup power. It can be stored for months. For companies operating global logistics networks or cloud regions spanning continents, hydrogen becomes an asset, not just a fuel. And SMRs make hydrogen viable in places where renewables struggle. Japan, South Korea, Singapore, and parts of Europe do not have the land or weather to scale solar and wind sufficiently. These regions are also heavily dependent on data centers and high-tech manufacturing. SMRs give them a path to produce clean hydrogen locally, without relying on imported LNG or renewable energy acreage they don't have. In the United States, SMR hydrogen systems could support emerging hydrogen hubs in the Gulf Coast, Midwest, and Mountain West. In Canada, SMRs could integrate with ammonia exports. In the Middle East, they could support hydrogen-based synthetic fuels for aviation and shipping. What makes this vision even more powerful is how the economics are shifting. With SMRs operating at high capacity factors, electrolyzer utilization increases dramatically. That lowers the cost of hydrogen. High-temperature electrolysis further reduces electricity consumption. Heat-assisted hydrogen production becomes cheaper and more efficient than electricity-only pathways. Under favorable incentives, SMR hydrogen could reach cost levels below $2 a kilogram, breaking the barrier that hydrogen developers have been chasing. With big tech's capital, these costs could fall even faster. Google, Microsoft, and Amazon spend tens of billions per year on infrastructure. Redirecting a fraction of that capital into energy systems would accelerate SMR and hydrogen deployment across the globe. The synergy doesn't stop there. Heat from SMRs can support industrial cooling systems for data centers. Hydrogen turbines can provide additional peaking power. Hydrogen pipelines can distribute surplus energy to nearby industries. Data centers become anchor customers for hydrogen hubs. Hydrogen becomes a buffer for variable workloads, balancing the energy consumption curves of modern AI.